Bringing real-time frame interpolation to SteamOS without engine modification requires intercepting Vulkan presentation calls at the driver layer. MAKO achieves this by pairing a custom C++ Vulkan implicit layer with a Python Decky Launcher control plane, using the licensed lossless scaling machine learning models directly inside Steam Game Mode.
The MAKO repository brings high-performance spatial frame generation to Linux handhelds and desktops. It unifies two former independent efforts, combining the Decky Loader UI integration with the high-throughput C++ Vulkan renderer engine. The project intercepts Vulkan swap chains to generate motion-interpolated frames in real time. When a game issues VKQ present KHR, MAKO's Vulkan layer intercepts the presentation queue before frame submission reaches GameScope. The internal adaptive scheduler analyzes frame cadence over a 3-frame temporal history window. If pacing is stable, it feeds frame pairs into the compute shader chain, issuing generated frames directly to the display pipeline.
Fixed multiplier frame generation often fails during sudden rendering rate shifts, such as jumping from a 30 FPS gameplay scene to a 60 FPS menu. MAKO resolves this with dynamic cadence recovery. By periodically requesting a native-only frame probe and confirming 3 consecutive fast samples, the scheduler automatically adjusts presentation pacing without dropping below baseline refresh targets.
Inside AdaptiveScheduler.cpp, frame planning operates without any runtime heap allocations. The method receives nanosecond presentation timestamps, updates a sliding history buffer, and evaluates discontinuity flags. When smooth cadence criteria are met, the engine returns a deterministic frame plan containing up to 3 normalized interpolation timestamps inline. Layer isolation is critical to avoid crashes when interacting with Proton, MangoHUD, or GameScope WSI. MAKO uses an explicit wrapper binary that strips competing frame generation environment variables, injects private Vulkan implicit layer manifests, and carefully manages pnext extension chains during swap chain creation to isolate graphics memory. HDR presentation requires explicit color space transformations before applying spatial frame interpolation. This GLSL compute shader converts HDR10PQ color representations into linear sRGB float values across 16x16 workgroups. The result ensures that luminance and motion vectors remain mathematically correct prior to frame synthesis. To enable MAKO on a native Steam game, add MAKO run %command% to the game launch options. For Flatpak applications like Heroic Launcher or EmuDeck emulators, MAKO provides dedicated Flatpak runtime extensions that bridge Vulkan layer manifests directly inside the sandboxed container path. The Python backend dynamically constructs shell wrapper scripts for each game profile. By generating explicit export declarations for profile fallbacks, GameScope WSI compatibility flags, and acquire timeout thresholds, the wrapper ensures reproducible environment variable configuration every time a game boots. MAKO interfaces directly with key Linux gaming components. Decky Loader handles per-game UI controls, Flatpak runtime extensions supply sandboxed Vulkan layer libraries, and integration modules allow seamless launcher hookup for Heroic, EmuDeck, and system Vulkan overlays like MangoHUD. Security and stability auditing reveals robust architectural choices in the C++ backend. Vulkan handles are wrapped in custom RAII-owned pointer templates to guarantee cleanup upon destruction. Furthermore, the core frame planning path performs zero runtime dynamic memory allocations, avoiding presentation stutter caused by GC or heap locking.
For severely constrained hardware like the Steam Deck APU, MAKO offers an ultra-performance profile. This setting combines a 75% flow scale, FP16 half-precision compute math, and lightweight policy resource allocation. In GPU-bound scenarios, this frees up rendering headroom and increases throughput by up to 30%. Analyzing MAKO reveals clear engineering decisions. The zero-allocation Vulkan layer and deterministic adaptive scheduler deliver steady frame pacing without adding runtime garbage collection pressure. However, users must own lossless scaling on Steam to supply lossless.dll, and published binaries currently target x86_64 architectures exclusively.
MAKO enforces hardware quality through strict pre-release validation scripts. The build system runs deterministic scheduler unit tests under address sanitizer, followed by automated AMD image quality regression testing across FP32 and FP16 compute modes before any local release archive is generated.
MAKO delivers an impressive, code-grounded solution for Vulkan frame generation on Linux. By pairing robust C++ backend engineering with seamless Decky Loader management, it pushes Linux handheld gaming performance forward. Check out the repository on GitHub to analyze the source code.